Okay, so I'd like to thank the organisers for giving me the opportunity to make this presentation and for fitting me into the schedule at a relatively late stage, so thank you very much. It's lovely to be back in Vienna, and so I will talk to you about colloids. I'm going to talk about two different kinds of systems, which I'll explain in a moment. But first, let me tell you about those who did the work. Now, this is actually from my first scientific trip to Vienna some time ago. The shirt is not in the state. I wouldn't wear it to give a talk like this. But you see, we did the honourable thing in Vienna, and we went to visit Boltzmann's tomb. But indeed, Ai Li Zhang, Jun Dong, and Ray Chang are a series of PhD students that have worked on colloidal gels and failure therein with myself and Malcolm Fires at Bayer over the years. Others involved in the project, Rob Jack and Himanshu Baumik, who are in Cambridge, and also Francesca Turci and Tony Liverpool and Abraham Morleon Amiva are involved in the active matter that I'll talk to you about towards the end of the presentation. Okay, these are the people, or these are the bodies that paid for the work, and now let me try to explain what I'm going to talk to you about. So I'll talk to you about gels, and I'll explain what I mean by gels, and I'll also, towards the end of the talk, get on to active colloids in extreme confinement, which may, if you look from far away, have connections to living systems. Okay, now, gels. Gels are one of the poorest defined words. They mean different things to different people. We recently had a meeting in Paris that some of you kindly attended, and there was termed by the good and great Itamar Procaccia the word gelology. Right? This is the discussion of different kinds of gels, and my gel's not the same as your gel, and so on and so forth. So I am going to talk about colloidal gels, and even within colloidal gels, there's differences. And so these can loosely be, certainly from an experimental point of view, colloidal gels can be weak or strong. But I'm going to talk about weak, by which I mean the interactions between the particles are a few times the thermal energy. We take the most simple colloidal system we can imagine, the hard sphere, and what we can then do is say, okay, we know what how hard spheres behave. The only thing for today that's relevant about how hard spheres behave is they form a glass when they are close, when they are packed at high volume fraction. What we're going to use is the next level up from hard spheres. So hard spheres are the simplest possible kind of colloid. We're going to make them sticky. All right, so we make them sticky, in this case, by adding polymer to them. But these sticky spheres are, the second simplest kind of colloid. So it's a very, very simple material. Okay, now I'm going to talk about experiments, and I'm also going to talk about simulations. And often it will not matter which is which. I have tried to remember to write in the graph sim or exp, depending on which one it is, but often it doesn't matter. But in any case, the experiments are colloid-polymer mixtures, the simulations are Brownian dynamic simulations. No hydrodynamics in this talk. I'm happy to discuss it, but I don't have any data with hydrodynamics today. Okay. Experiments do feature hydrodynamics, yes, yes. Yeah. Okay, so the gels that we are dealing with undergo arrested spinodal decomposition. So let me remind you what spinodal decomposition looks like. The material demixes into two phases. And if we let it run and run, then it'll completely demix into, in the case of the colloids, a colloid-rich phase and a colloid-poor phase. It doesn't do that, it becomes arrested. So the gels, we've seen pictures of these sorts of things previously, yesterday afternoon. This is my picture of a colloidal gel, okay? And what we understand in general, I hope we would agree, from one of my heroes, Paddy Royall, at least I got this from him. He says the perceived wisdom of material science is how the microscopic structure determines the macroscopic properties of the material. So that's a sort of mantra that we'll take forward through this talk. The central dogma. Okay. So in particular, the ways that small groups of particles can organize are into clusters. So we said the particles are sticky, so 5 sticky spheres will make this, 6 sticky spheres make this, 7 make this, and so on. Okay, so we can, long ago it was determined that these are the structures, that these clusters are what sticky spheres form, and in an experiment some time ago, we identified them. So this is experimental data, these different colors. So the white are these triangular bipyramids, and for example, the green is this 10-membered structure, which I call the defective icosahedron, but there's different shapes. What's important about these is these things are all rigid. Okay, so all the particles are bonded locally to enough other particles that they are rigid. And that if the gel is made out of these rigid groups of particles, then the whole structure is rigid, and it's a solid. So that's good. We understand why gels are solid, or at least reasonably solid. They're also far from equilibrium. Okay, so I said that the equilibrium case is a complete phase separation to colloid rich and colloid poor. What does it do over time? It slowly ages. Okay, so these are some simulation data running over a considerable time by simulation standards. And what I want to emphasize here is that the arms that the gel is comprised of get thicker, right? So here, this arm is really quite thick. It's maybe 10 particles across, whereas earlier on, it's fewer particles across. Okay, so the thing is slowly coarsening over time. We understand that this local structure should control the macroscopic properties of the material. And it does. So I am not a rheologist, okay, and I know that there are experts in the audience, but anyway, here is G prime and G double primed, and all I want to tell you is that this one's increasing, okay? The material is getting stiffer over time, and it's slowly aging. And we can also, sorry? Well, I was wondering that when I made the graph, and I checked, and I might have switched them. I might have made an error when I made the graph manual. That is entirely possible. Okay, but I had a funny feeling that somebody might say that, and I thought, well, should I turn it round? But yeah, it's quite possible. I made an error when I plotted the graph. But this should be G primed, and this should be G double primed. That is entirely possible. Okay, but I said I'm not a rheologist. But what I do want to say is that this line's going up. What is also happening is that, as I said, the arms are getting thicker. So this is a measure of the width of the arms in the system, and also the local structure is changing. So here, this is a measure. This green one here, this 10-membered structure, is becoming more and more prevalent. Okay, so this thing's so there is a change in the local structure of the material. It's getting stronger, it's getting stiffer, and that's all good, right? So we know what gels do. So unfortunately, there's more to the story. So this is a macroscopic gel. This thing is about 5 centimeters high. I'm going to play a movie of it. In these little these things are tracer particles. They're not terribly important, but we can actually follow what happens reasonably locally. They're about half a millimeter. No, they're about 100 microns in size, these tracer particles. But anyway, the movie will run over about 30 hours. This is the time. And so for a long time, nothing happens. It's just sitting there getting stiffer and stiffer. And still, for some time, nothing happens. And suddenly, there's a failure. Okay, suddenly, this very simple material that I've told you that we know everything about has just suddenly failed, which is a bit unusual given that it's getting stiffer and stronger over time. The blue. Right. So the blue is the light. So it's lit with it's an emulsion. The colloids are lighter than the solvent, and so it creams. So the effect of gravity is to move it up, which is what you saw. But the blue is the illumination that's used to take the moving. The system is PDMS. It's an emulsion. It's a PDMS emulsion in an aqueous solvent with an appropriate polymer which goes by the name of HHX. It's hydroxyether cellulose. The particles are 500 nanometers roughly in this system, and if I have the gravitational length of a single particle is about the size of the system. So if I did not have the polymer, this thing basically doesn't sediment at all. It just sits there. But by adding the polymer, I get this gel, and I get this failure that we see. And the direction of failure is up because the particles are lighter than the solvent. So this is somewhat problematic, given that we think that we understand the material quite well.
Sorry. So in this particular example, and I guess it's typical, failure is happening from the boundary. Is that something you're going to comment on?
I will get to it. But what I will say is, so we think that the failure seems to happen at the top. But to muddy the waters, there is earlier work where the colloids are heavier than the solvent. And in that case, the failure also starts at the top. Okay, so what can we do to understand this? Well, this is, a computer simulation of a macroscopic system for hours and hours is not going to be easy. But what we can do is we can look at the fundamental, what we claim is the fundamental mechanism or fundamental example of failure. So this is a single strand, and it's organized as a cylinder, and we're going to measure the Irving-Kirkwood stress in it. And we're pulling on the strand above and below. These are brand new dynamics simulations, and at some point up here, if we wait for long enough, we get something that we start to see that the strand is going to thin somewhat. As it eventually thins, I hope you can see that it's starting to thin here. It's getting redder, or flickering into redder from time to time where there's more stress locally, and then it fails. Okay, so this is a necking instability which can be observed in other materials, but at least we can claim that, okay, this is a way by which a single strand of the gel can fail. One thing that we might ask is, can we predict that failure? So we've got the whole microscopic process. We know the stress on the particles. We know their structure. And so if we look at the loss of neighbors, then there's really nothing to see until it fails. So I've got two lines here. The red is a bit of the strand where it doesn't fail. The blue is where it ends up failing. And what you see is there's nothing really to see until it finally fails. With the local structure, though, there is a departure from the bit that doesn't fail, the red, much earlier. Okay, so somehow the population of these things in the strand is much more sensitive measure to failure. And in fact, if I was being optimistic, which I am going to be, then even at a strain of 0.1, then I can already claim that there's a difference with respect to the case that doesn't fail long before it actually yields. Okay, so we can see evidence of failure before it fails in simulation. What about experiment? So we saw, Thomas.
Evolution of the stress within your strand over time?
Yeah, that was, yes.
As a
I have plotted it. I haven't got it in the. It comes and goes. So what happens? So as the strand is pulled, there are little rearrangements. So there are plastic rearrangements. So the stress will increase, and there's a plastic rearrangement. It decreases, and Then as we pull it more, it will increase again, and there'll be more plastic rearrangements. Suzanne?
There were some predictions a while ago about when necking occurs in viscoelastic filaments, and so in solids, there's this thing called the Consider criterion, which says when the force as a function of extensional strain goes and has a negative slope, you get necking. But with viscoelasticity, it seems to be more when the I should say, I actually made these predictions and I've forgotten them now. It's when the extensional stress as a function of strain goes through a point of inflection, so it curves up and then it curves down. So I just wondered if you'd looked at that, if you look at the stress as a function of strain signal, and if you see a point of inflection around the time of necking. Or maybe worth doing if you have.
All sorts of fluid for us. So that is to say that it's kind of relaxing, so we pull it and it relaxes, we pull it and it relaxes. If that should still show it. No. Yeah. It's getting longer. No, so it's just a filament, right? So we're stretching it. So I don't show it in the movie, but particles are disappearing out of the top and the bottom. Or to put it another way, we're stretching the box. Yeah. But then there's nothing in the side, so it's just getting thinner. So, sorry, at the point, where it forms the neck, it gets thinner, but... yeah. No, we just make it longer. So we do not conserve volume.
Break?
Correct.
Is that correct?
Yeah. If we don't, it's a glass. Well, sort of a glass, right? So nothing happens if we don't. Nothing happens if we pull on it. So at an experimental level, then what we have, again, following the talk from yesterday, we take inspiration from granular material, and in particular these photoelastic discs that show the force chains. So we wanted to try to do something like this in the colloid experiments. But this is not that straightforward. These things are centimeters in size, and the colloids, for sure, are not centimeters in size. And but luckily, in her PhD, Jasna Bruch had looked at a system that we can utilize to go towards the colloidal length scale. So she developed a system, in fact, the same material I just mentioned, PDMS, polydimethylsiloxane emulsion droplets. And what she did was she added this solvatochromic dye, Nile red. And why do we care about that? Well, what solvatochromic means is that the fluorescence of the dye depends on the chemical environment that it's in. So if it's in the middle of the droplet, it's green. And if it's on the edge of the droplet, it's red. And if it's at a contact between two droplets, it's really red, or it's very intensely red. So we can image this. We have to use very fancy imaging techniques that I don't have time to get into now, although I can if you want to ask questions. But the droplet channel looks like this. And then we have this separate channel for the contacts, which you can see between the droplets. And then we obviously image both at the same time. So our data looks like this. So we can start to see contacts between the droplets in a colloidal system, and the intensity of the contacts reflects the force between the droplets. So our data looks like this. These are coordinates with contacts between them, and we can analyze the data to obtain something that's a bit like a particle level measure of a stress tensor. So we can measure the forces between droplets of a given, for a particular droplet, measure the forces from its neighbors, and in this way we can come up with a stress tensor, or something like it at the local level. We can then...
It becomes red in the contact. Okay, but can you really quantify the effect of stress? I mean, How do you go from the intensity?
I'll show you a graph in a couple of slides' time, which may address your question. The pictures look nice, as they often do. So this is the negative stress, sorry, the negative trace, what we call the stress tensor, and this is some connection to local pressure. And so, for example, here, the yellow would be high pressure, and here we're measuring the number of tetrahedra the particles in, so a measure of local structure. So this is then relatively well structured, as is this, and then on the other side here, we've got a relatively high pressure. So there's a correlation visually between local structure and
Else question. If you can measure the force, then this is the stress tensor. It's just the virial stress tensor. So are you saying you can measure the force, or you're approximating the force to get the stress?
I've got a couple of slides time, right? So, which is actually this slide. So, are we measuring the stress or not? So what we have the contact volume, and we claim that the contact volume. Well, one scenario is the contact volume is linear in the force between the droplets, and so you can say, okay, well, this is the probability distribution of the contact volumes that we have in the experiment, and we can do a simulation which we might claim was the same thing, where we know everything, and if we are doing a good job of measuring the stress through these contact volumes, then these graphs should be the same, and they're not a world apart. So we're measuring something that's definitely related to the force between the droplets. Whether it's absolutely the force between the droplets, I think we need to do a better job of we need to do more to be absolutely clear about that. Well, that's where we are at the moment.
Of the force.
Yeah,
presumably.
We can measure things that look like force chains inspired by work in granular matter, and if we do that, we actually see that there is a difference between the simulations and the experiments. But of course, as Shri pointed out, then the simulations do not have hydrodynamics. The interaction potential isn't quite the same, so maybe that can explain the difference here between the experiment and the simulations in the distribution of lengths of the force chains. Okay, Roberta, how long do I have? Okay, thank you. All right, so we can do something about understanding stresses in the experiments. We can take that to failure. We can understand something about failure in computer simulations. But all this is at a microscopic level. And the movie that I showed, the blue movie, is a macroscopic system. So what can we do to try to understand the failure in the macroscopic system? We're not the first to look at this. There was really significant work done by Laura Stars and Wilson Poon a long time ago. What they're doing here, they're taking the same, or essentially the same system that we have, and they're using dark field microscopy, and they're measuring these things. They call them streamers. They're measuring the velocity, all right? So this is a little bit like the movement of the tracer particles that I had in the movie that I showed. All of these pictures, the pictures are not linear in time. These pictures are all around the point where the gel fails. Well, there's definitely something happening in the system, and somehow there is the growth of something. But macroscopically, as you saw in the movie that I showed, there's nothing to see. All right. So how can we presumably the gel collapse has got some sort of microscopic origin, but how do we deal with a microscopic origin particle level in something that is centimeters in size? Well, what we did was put the whole thing in the microscope. So, and we call this multi-scale confocal microscopy. So this is the macroscopic picture, and this particular system failed after 180 minutes. So this is all long before failure. So these are similar images. This is showing the whole thing, the scale was millimeters, and we can image the entire thing in the microscope, but we can also, because we've got microscopic resolution, we can zoom in, and there's really not very much to see. This is an artifact. So there's at short times, there's really very little to see, but we can zoom in to go right down to the structure of the gel. Okay, so this is essentially the same thing as the microscopic pictures I showed. This is the colloid-polymer mixture that's slowly undergoing spinodal decomposition. But because we've got this microscopic picture of the whole system, then once it does start to exhibit something going on at the top, this thing here, we can see it, and we can look closely, and we can see what it is. Now, what it is, we've fluorescently labeled the colloids, so the dark stuff here is solvent with colloids entrained in it. And if we now, at longer times, then we start to see even more development of these things. And so we have these streamers, which are solvent, pure, well, essentially solvent, but with some colloid-rich material entrained into it. But this is what the streamers are. And they are slowly making their way from the top to the bottom of the gel. So we can image them. This is what it looks like as they move down through the gel, and it's a load of solvent ripping away the material of the gel and slowly making its way from the top to the bottom. So how does it work?
Or you integrate
Good question, Laurence. I claim that we get the whole thing. Of course, we don't, because you're right, it's a 2D slice. So this is a 2D slice from a 3D system. So we have it all in 2 dimensions, but there is a 3rd dimension that we do not get the data in. Okay, so what do we think is happening? Well, I said that the system was undergoing phase separation, and I hope you can see, but anyway, my claim is that at the top, there is enhanced phase separation. Phase separation occurs more rapidly at the top of the system, and so what's happening eventually is that we get the formation of a solvent-rich droplet. And that solvent-rich droplet is heavier than the gel. And as it gets bigger and bigger, at some point, well, it's got a gravitational force going down, which is given by this. This is the volume fraction. This is the volume of the droplet and the density difference between the droplet and the density difference between the solvent and the colloids. And that then exerts a stress on the surrounding gel, which scales in this way. And so my point is that there's some radius of this droplet of solvent-rich material where it's become big enough to break the gel. Now, the gel's yield stress is about kBt per particle diameter cubed, right? So once these two things are the same, then the droplet should start to head down through the material and will become the streamer. And it turns out that is something like 50, when the droplet's 50 diameters in radius, then that's when this condition will be met, which is reasonable. This doesn't have to be an explanation, but it's at least reasonable. I'm sorry? That's just that's the yeah. It tends to be about this. But so the attractions are a few kT, so like 5 kT, something like that. And that's what we measure, admittedly from simulation, but I believe it. Okay, so that's the explanation for that particular regime of gel collapse. It's not the only regime of gel collapse, so that's what I want to tell you about today. Anil.
Describe this destabilization is you have this drop going down. What would be the initial destabilization mechanism? I mean, do you think that...
Right, good question. Right, so are you saying why is there accelerated aging at the top? I've just stated that, and anecdotal observation of colloids in microscopes has that at the very top is the interface between the top of the suspension and the air. And there's little tiny bits of thermal instability, well, thermal fluctuations. You always see when you look in the microscope at the top of the system, the colloids are moving hugely, much more than they do in the middle. And that's just an experimental observation. So somehow there's just more going on at the top than there is in the middle.
Rather than having
I think the phase separation just is happening quickly.
a nucleation and not an density.
Composition, so it doesn't actually need to, in a sense, it doesn't need to nucleate.
It's not nucleation.
Well, if you have droplets that form, they form by some kind of nucleation process, right? Or either you nucleate.
The thing's unstable, so it's just a question of how quickly it's doing it.
No, the question is what is the mechanism of instability? So is it?
It's thermodynamic. It's the gel is itself is in a thermodynamically unstable region of the phase diagram.
A specific wavelength at the surface.
All right, okay, yeah, that's a point. Sorry, Aaron, that's a really good point, and you don't see that. So there is something to nucleate with it. You're right. Sorry, I take your point.
Related to that, do you see the droplet coalesce when you measure the size of your droplets?
We haven't seen it. We haven't seen it, but we haven't tried very hard to see it. So that doesn't mean it doesn't happen. It just means we haven't seen it. Okay, so in the last few minutes, I want to try to connect to those. Thank you, Roberta. I want to try to connect to those to work with more biological systems. Okay, so this was very dead. I completely accept that. So let me tell you about a difference between a passive system and an active system that superficially look very similar. Let me first tell you about the passive system. These are hard disks. Okay, so these are colloids, they're in 2 dimensions, and the red dots are optical tweezers. We're going to animate the optical tweezers such that so they're still in optical tweezers, I just didn't render them. These particles are pushed around by optical tweezers, and this thing is transmitting torque to the middle of the assembly. So this, if you like, is a very small rheometer, and what we're seeing here is that there's transmission of momentum between this layer and this layer and this layer and this layer and so on. So that's fine. Now, the mechanism of slip, we understand that it looks like this. So the outer layers are going faster. I hope you can see this layer is overtaking this one. If you wait for long enough, this layer overtakes this one and so on. So the outer layers are going faster. And so we start with these 2 yellow particles. They go a little faster than the particles on the inside and faster again, and eventually we have a similar situation to the one we started with the yellow particles having moved 1 diameter further than the particles on the inside layer. So that we claim is the mechanism of slip in this system. This is a passive system of hard disks. It's just driven at the boundary. We can compare that to an active system. This is a reasonably well-known active system. These are Quincke rollers. These are the colors of the hexagonal order parameter that we saw in the previous talk. They're mainly in the movie because they look pretty for now. But the particles roll. A DC electric field is applied to them. They roll on the substrate. But I think you can model them or think of them as active Brownian particles with an alignment term. And also, this particular version of Quincke rollers, you see they condense. They condense into these things we call amoeba, but there is an attraction between the particles as well, which is electrohydrodynamic in nature. Anyway, so this is a reasonably well understood active system. We can confine it. Okay, so here are the Quincke rollers. They are confined at various particle loadings into small regions, and they are, as you see, active in those small regions. So this is kind of like what I just showed for the passive matter, except that it's active. All right, it's a similar number of particles. They're also a similar size, and of course they've got a hard core. So what does it look like if we have a magic number of 61? Then when they become active, they form a hexagonal configuration. and the thing rotates as a rigid body. Then, if we start to speed things up, what you see is that the particles are they're not all rotating at the same rate. And in particular, the interior is rotating, at least with respect to these yellow ones, the interior is rotating faster than the exterior. We can speed them up some more, and we see again a fairly similar behavior, and we can speed them up even more, and then we break the hexagonal order, and we end up with something that actually visually looks almost the same as the passive system that I showed you, except that what's going on in terms of the relative rotations of the layers is completely different to the passive system. We have Tanny Liverpool has come up with a discretized tone-of-tune model which qualitatively describes what we see. So let me explain what's happening here. This is the layer, this is the angular velocity, and so if they're passive, they sit here. We then have the rigid body case, and as we increase the field strength, we start to see that the inside rotates faster than does the outside, which is just what I showed you in the movies. But the lines here are the tone-of-tune model, and the data points are the experiments. And so we claim that we've done a reasonable job of capturing the behavior in this active matter system with the tone-of-tune model. Okay, so let me wrap up. I've told you that we understand how colloidal gels of the type that I'm interested in here are rigid. I told you that they got stiffer over time, and then I showed a movie which rather contradicted that in the sense that although the material is getting stiffer over time, a macroscopic gel fails. And I talked about microscopic mechanisms for failure with computer simulation and also by obtaining the forces between droplets in experiment. But to understand the failure of the gel, I talked about this multi-scale confocal microscopy to image the nature of these streamers that cause the failure of the material. And finally, I talked about rotation and rheological behavior and failure or yielding in active colloids. So with that, I'd like to thank you for your attention, and I'll take any questions.